Oh, shit. One leg is broken for my little dude. All right, I want to say one little thing about Section 10.2. I'm going to officially make Section 10.2 extra credit. So we'll see if anybody pays attention to what I'm going to say about it. So let me say that again for those of you who woke up when I said the word extra credit. It was at the end of my sentence. So 10.2. Okay. Yes. Yes.
So we didn't actually have to turn that in.
If you do, you might get extra credit. And you don't have to. If you did it, you might as well turn it in and see what the hell happens. Okay, so real quick. A couple of quick things. What's this? What's the formula for this? What does that mean, first off? What does this mean? Standard deviation, that's a good start. Of sample size of whatever, right? Standard deviation of all samples of size n. And what's the formula for it?
Standard deviation divided by the square root of n.
All right, now, real quick, just stay with me. How many standard deviations do I have up here? One. I love it. I have one standard deviation. Okay. Chapter 10 is all about when you have two samples. So in real life, when I create a drug or something, do I have any idea about the average time it takes for that drug to start working? No, I don't, because I just made the damn thing, right? So what do I do to test it? I have at least 3 groups. But let's just pretend like it's 2. One group gets the drug, and the other group gets a little bit of sugar, right? In the form of a pill. And I want to compare the 2 groups. And really what it breaks down to, just to really cut this to the quick, is I want to see how far apart the 2 groups are. So what do I want? If I'm the creator of the drug, I want my drug to how compare to the placebo. I want my drug to actually work at a higher rate than the placebo drug does. You guys got the placebo, by the way. All right, that's why a lot of you guys are missing, I guess. Oops. All right, you guys with me? A little bit? Okay, so I need to make room in this equation for 2 standard deviations, because I'm talking about 2 populations. The population that would get the drug and the population that wouldn't. So I need room for 2 standard deviations. I love you guys. I can look in your eyes, you're all like, I'm going to pretend to pay attention. I'm just going to keep going. So here's the first thing I do to make room. I make this one big-ass square root. So there's the square root of n, right? Is that cool? So far it's the same stupid formula. Square root of what is sigma? The square root of what is sigma? The square root of what is 2? 4. So 2 squared, right? Square root of what is sigma? The square root is sigma squared. Yes, is that cool? What's the square root of sigma squared? Sigma. Yes. All right, I like it. Why is it not plus or minus? Because standard deviation has to be positive. Okay, I like it. So what I do in Chapter 10, in Section 10.2, is I make it this. I double that. How many samples am I taking? 2. So how many populations do they represent? 2. So I've got, basically, my Z star formula becomes twice as big. So normally Z star in the past was X bar minus the mean of the X bars divided by the new standard deviation, right? That's what it was. So now it's the same thing. It's going to be the difference between the 2 samples minus the difference between the 2 populations divided by big-ass square root. In fact, let's be more specific. Let's put S's in there. This would really be T star. So see how everything here is doubled over there? Do you guys see that? There's one sample taken here. Well, I'm going to take two samples here. Gets the drug, doesn't get the drug. Good luck. And then here's the minus the one mean for the population. Well, there's two freaking populations now. Here's the one standard deviation. Well, there's two. So it looks like this huge Z-star brand new formula. It's the same damn formula. It's the same damn formula as always, to be honest. If you don't believe me, it's okay. What are we always fighting against? What am I fighting against when I give one group the drug and one group a sugar pill? What do I not want to have happen? I don't want my drug to work equally well as a sugar pill. You with me? Because then they'll just buy sugar and take that. I'm going to get better, right? Yes. I don't want my drug to end up working just as well as a sugar pill. I want my drug to work better than a sugar pill. Are you right? Right? I don't want the average effect of my drug to be equal to this. So that's what I'm fighting against. I'm fighting against this. So my null hypothesis would be this, that they're equal. And my alternate is they're not equal somehow, right? Well, if mu1 equals mu2, what is this? If mu1 equals mu2, what's this? If mu1 equals mu2, what's mu1 minus mu2?
0.
I like some of you guys are like, I'm going to talk to you. That's 0. Okay. So here's the official formula. If you look at your answer key for the last test, I put this formula on there for number 6, I think it was, the one that was absent from your test. It's the difference in the sample. So look at this. Look right there. This is what I was talking about. If I give one group the drug and I give one group the placebo, I want this difference to be big. The bigger this difference is, the more evidence I find that they're not equal to each other. The bigger this difference is, the bigger this is. And why is this good to be big? Because that means it's far away from the middle. It means that it's evidence that it's different. Now for my drug, I'd want it to be better, not just different, because different could mean worse. That would suck. Taking a sugar pill is better for you. Oh, shit.
So
all right.
The claim would be that the sample mean is different than... Or
You would never make a claim about sample.
Oh, okay.
Yeah, the claim could either be, in my case, it would be mu1 less than mu2 if my ones were my drug. I want the time it takes for them to work to be less than. Or, whatever it is I'm measuring. Yes. Okay, maybe. So all the 5 steps are the same. If you're going to do this extra credit, I will tell you the degrees of freedom get a little freaky. There's a formula in the book. Screw that formula in the book. Degrees of freedom would be just n1 plus n2 minus 2. Does that kind of make sense? What do you do when you have one sample? What's the degrees of freedom? N minus 1. So now I add the 2 together, subtract 1 for each. So it's the 2 added minus 2. Now there's a very complicated formula in the book that it actually is technically correct, but this is fine for those of us with crazy teachers making us do it by hand. Okay, so if you want to, you can try that out. It's exactly like Chapter 9. It's just when you get to Step 4, you got this big-ass formula to put all the sample information in. If you want to. If you don't want to, that's okay. All right. So that's my truncated lecture on Section 10.2. Yes, because you assume that this is true, so that would mean this is 0. Now, in real life, there are other sections in Chapter 10. In real life, you have situations where your claim is it's 9 more than this, and then this wouldn't be 0, but I didn't assign any of those. Yeah. Okay. So if you're not going to do that section, shake it off. Hopefully, I'm not going to sing to you. Hopefully it made a little bit of sense. taking two samples, so guess what? You need room for two pieces of information everywhere. That part should make hopeful sense. I use the word hopeful a lot. Hopeful. Okay. All right. So what we're going to talk about today, what I want to focus on, I'm actually going to jump to chapter 12 to kind of give you a little bit of a break, because I know hypothesis tests can be like, ugh. So chapter 12 is a very nice little section about something called correlation. And then we'll come back to chapter 11, which is as evil as it sounds. It's like bankruptcy, but it's it's a brand new distribution called the chi-square. Right? It has nothing to do with Dragon Ball. Don't get too excited. But correlation. So when I say correlation, I mean, what do you guys think about when I say correlation? Besides, tell me what the shit that means, Jeff. Does anybody have any idea about correlation? Two things are correlated. Connected. There's a relationship between the two things. I like it. They kind of make co-related. So if they're related in some way, that could mean one affects the other one, but correlated says they might affect each other. So it's sort of like, here's an unfair kind of correlation. Let me start with a dumb correlation. I go around and watch people playing basketball, and then I say, playing basketball makes you tall. This is really interesting. Right? So if you're short, you'll start playing basketball, you get taller. Right? Why is that a dumb correlation? What's the obvious direction that should go? Playing basketball doesn't make you tall. If you're tall, there's a higher chance you'll play basketball, right? So notice they didn't say a damn thing about short people can't play. Because I play and I'm not exactly tall. You've got to have a good fadeaway jumper to get anything in there, but or pass between people's legs. So that was obviously, now, you guys agree with me, that was stupid as shit, right? It was really, really dumb. But there are situations where we have no idea what affects what. And we'll make just as stupid conclusions because we don't know. And there's no obviously we know what happens there, right? Playing basketball doesn't make you taller, that's dumb. But there are things that are nowhere near as obvious that we see correlations between. So, for example, here we go. This is true. In areas where there are more cell phone towers, the fertility rate is higher. The number of babies born is higher. Let me say it like that. So in area, this is true. You listening to me? This is true, and it's where there's more cell phone towers, more babies are born. Do cell phone towers cause people to have babies then? Where will there be more cell phone towers? Where you have more people. And when you have more people, you're going to have more
Cell phone towers.
Sure, but now keep going the next step. You're going to have more babies, right? You guys with me? Yeah. Yes, a little bit? I always hate, you see this all the time still nowadays. They'll say something stupid like, more people in California are in jail than in Vermont. And I'm like, there's probably more people in jail in California than are in Vermont, period. Right? Why is that an unfair comparison? Because there's more freaking people in California, so there's probably more everything. There's more people that like Brussels sprouts in California than, of course, there's just more people, right? So, but that level of stupid is out there, and if you don't know what the shit you're supposed to think about when you read stuff like that, you're automatic. You're gonna be like, what's wrong with California? Get out of here! Oh my God! No, it's about the same rate of incarceration, right? Okay, maybe. So, what we want to do, let me give you this. This will make this easier to talk about. Have some visuals. Oh, now the AC is on. I love it. Shit. Let me just put this caveat out there. This is not my suggestion for an experiment. If you started reading through this.